Despite the promise of artificial intelligence, deploying machine learning models into production environments often uncovers a complex array of challenges. The journey from a working prototype to a robust, scalable, and maintainable system is fraught with technical and operational hurdles, frequently leading to performance degradation and missed objectives. One of the most insidious problems is model drift, a phenomenon where a model's performance deteriorates over time due to changes in the underlying data distribution. This can manifest as concept drift, where the relationship between input features and the target variable changes, or data drift, where the statistical properties of the input features themselves evolve. Unaddressed, model drift renders once accurate predictions unreliable. To counter model drift, sophisticated monitoring systems are essential. These systems track key performance indicators such as accuracy, precision, and recall, alongside input feature distributions and prediction confidence. Statistical process control techniques, like Shewhart charts, can identify deviations from expected behavior. Advanced methods include A/B testing live models against challenger models or retraining on fresh data when drift metrics cross predefined thresholds. Another significant obstacle is infrastructure complexity. Machine learning workloads demand dynamic resource allocation, specialized hardware like GPUs, and often involve distributed computing frameworks. Managing environments across development, staging, and production, while ensuring consistency and reproducibility, introduces substantial overhead and potential points of failure. Containerization, primarily through Docker, provides a robust solution for packaging models and their dependencies into portable, isolated units. Orchestration platforms like Kubernetes then manage these containers, automating deployment, scaling, and operational tasks across diverse clusters. This ensures environmental parity and significantly reduces deployment friction, making ML systems inherently more scalable and resilient. Ethical AI considerations present a critical challenge. Biases embedded in training data can lead to unfair or discriminatory outcomes when models are deployed, impacting sensitive areas like loan applications or healthcare. Furthermore, a lack of transparency in complex models, often termed the black box problem, hinders trust and accountability. Addressing ethical concerns requires a multifaceted approach. Explainable AI, or XAI, techniques like LIME and SHAP provide insights into model predictions, helping to understand feature importance and local decision boundaries. Bias detection and mitigation strategies involve rigorous auditing of training data, fairness metrics like demographic parity or equalized odds, and techniques such as resampling or adversarial debiasing. Data versioning and governance pose persistent difficulties. Machine learning models are inherently dependent on data. Tracking changes in datasets, ensuring data quality, and maintaining an auditable history of which data version was used for a specific model iteration are crucial for reproducibility and debugging, yet often overlooked. Specialized data version control tools, such as DVC, integrate with existing Git repositories to manage large datasets and track their lineage. Robust MLOps platforms often provide built-in data governance capabilities, ensuring that data pipelines are monitored, data schemas are enforced, and access controls are properly managed, thus maintaining data integrity throughout the model lifecycle. Reproducibility and auditability are foundational yet frequently elusive. The ability to recreate a model's exact behavior and predictions at any point in its lifecycle, given the same code, data, and environment, is vital for debugging, compliance, and iterative improvement. Without it, diagnosing production issues becomes a near impossible task. Experiment tracking systems are paramount for achieving reproducibility. These systems log every aspect of a model. Training run, hyperparameters, code versions, input data hashes, metrics, and generated artifacts. This comprehensive metadata management enables developers to precisely reconstruct any past experiment and understand the evolution of a model's performance. Effective observability and monitoring are essential for post-deployment operational intelligence. It is not enough to simply deploy a model. Understanding its real-time performance, resource consumption, and potential issues within a complex distributed system is critical. Failure to monitor leads to delayed problem detection and reduced business value. Comprehensive monitoring dashboards, integrating metrics on model performance, infrastructure health, and data pipeline status, provide a unified view. Automated alerting systems, configured to notify stakeholders upon detection of anomalies or critical thresholds being crossed, enable proactive intervention, preventing minor issues from escalating into major outages. Integrating these MLOps practices requires a systematic approach. Establishing clear MLOps pipelines that automate the entire machine learning lifecycle, from data ingestion and model training to deployment and monitoring, reduces manual errors and accelerates iteration cycles. This continuous integration and continuous delivery CI/CD for ML fosters agility and reliability. Beyond tools and processes, organizational culture and collaboration are critical. Breaking down silos between data scientists, machine learning engineers, and operations teams fosters a shared understanding of responsibilities and goals. A culture that prioritizes experimentation, learning from failures, and continuous improvement is fundamental for successful MLOps adoption. Overcoming the inherent challenges in MLOps is not merely about adopting a set of tools. It is about cultivating a discipline that transforms sporadic model development into robust, scalable, and ethically sound machine learning systems. By systematically addressing model drift, infrastructure complexity, ethical considerations, and data governance, organizations can unlock the sustained value of their AI investments.